Yeah, so Kishore, go on.
Yeah. Uh, yeah, so can you guys see my screen? Hello?
Yeah, Kishore.
Yeah, we can.
Okay. Yeah, okay. Cool. So, hello guys, welcome to another session in Zero to Hero in Machine Learning series Summer School. And today we'll continue from where we left off in the previous session, that is Intro to DL, and this will be the second part. And so let's look at the agenda for today. Today we'll first have a recap of what we learned in the previous session, which is forward propagation. And then we'll look in detail about some of the activation functions. And then we'll go to cost functions. And then we'll look at something called the back-propagation, which is important for training the network. And then we'll look at optimization algorithms to converge the networks faster. Okay, so going to the forward propagation. So let's have a small recap. So consider this small neural network. So here I have 4 layers, and this one is the input layer, and we have 2 hidden layers in green, and then one output layer. What do we do in forward propagation? So we feed in information uh, through these input nodes, and that information passes through these connections to the next hidden layer. Then from that hidden layer, again it passes through the layers conjugatively, and then it finally reaches the output. And in between we have some mathematical processes like multiplying the values with weights and adding biases. Uh, and so this is basically what happens in forward propagation. So yeah, and before moving on, so this is super important. So this is a notation that we are going to use, and this will be this is important for understanding the back propagation, which we'll look at later in the session. So what is the notation that I'm using here? The notation is so first one is AI, and A is the input. Sorry, yeah, A is the value of the input node, value of the ith input node. So we can see here we have A1, A2, A3, and A4. So AI will be sorry, yeah, A1, A2, A3, and A4. Next we have weights, and weights are represented by W with the superscript K and subscript Ij. And this represents the weight of the connection between the ith node and the of the kth layer and the jth node of the k plus 1th layer. So I'll explain it. So suppose let's take a random connection. So let's take this one for instance, and this weight will be represented as, so we have ith node of the kth layer. So suppose this is the kth layer, so k will be 1, and here for this one k will be 2, and k will be 3 for this one, and k is 4. So this weight is represented as W with the superscript 1, and it is connecting the 4th node of the first layer and the 2nd node of the 2nd layer. So that will be W with superscript 1 and subscript 4 2, the values of the I and j respectively. Next we have bias value, and that is represented as B with the superscript K and subscript I, and that's the bias value of the ith node in the k plus 1th layer. So here if you see here, let's take this node for example. We have a bias of say B, and it is represented as B with a superscript K, and that represents K plus 1th layer. So this is B1, right? So this will be B1 with superscript 1 and subscript 2, because it's the second node. So this will be B12 and this will be B11. And similarly, this will be B21, this will be B22. And yeah, so and for the inputs and the outputs here, we don't have any biases. Yeah. And this is basically what happens in forward propagation. This is just a recap. So basically we feed in information through the input layer. And here I've represented all of them as matrices. So we feed in information through the input layer, and then we perform some mathematical operations like multiplying it with the weights and then adding biases. And then we plug the value into the activation function, and then we this value will be the input to the next layer, and similarly it goes on, and then finally we get the output. And at the output you can see we don't have a bias, so we don't add that plus b here. And one thing to note here is that all of them are matrices. uh, so here this w times x, this is not just normal multiplication, this is a matrix multiplication. Yeah, and this activation function, this is an element-wise operation. So we take each and every element and then we put it in the activation function and we get A2. So that's about forward propagation. And next, Skandan will explain more about activation functions in detail. Over to you, Skandan.
Yeah, so can you see the presentation?
Yeah, maybe could you be a little louder? Slightly.
Sorry?
Maybe could you just speak a little louder? Otherwise, it's fine.
You mean the zooming?
No. I'm asking you to speak a little louder.
Oh, louder. Okay, yeah.
Yeah.
Okay. Yeah. So now we'll look into activation functions. So the main purpose of activation functions is to introduce some sort of non-linearity into this network. So if we see what how they work, basically, let's look at the values at the previous layer. So you have some outputs x1, x2, so on to xn, which are the outputs of the previous layer, and they are getting multiplied by their corresponding weights and being summed. So that's the weighted sum which we just saw. After which you're adding the bias of this particular node, and this resultant value is being put into the activation function, and that's what is passed on to the next layer for forward propagation. So it's first the weighted sum followed by adding a bias. Then you make the activation function act on that resultant number. Then this is used for further propagation along the network. So if you look into the reason behind this, so this activation function is not, it's not an arbitrary decision to include this. So if let's consider what happens if we don't include any activation function. So supposing we had a neural network where the only operation it could do was to have some linear combination of weights when it propagates from between every two layers. So what you would get is a resultant of the resultant value you get would be a composition of several linear operations. Like for example, if you add, like let's just take for one variable, if you add something like ax plus b, and that x itself was some cx plus d for the previous layer, if you keep composing this repeatedly, the resultant function you get will also be a linear function. So if we don't have any activation function, our neural network can only behave as a linear map. So it will only be able to classify linearly separable data, or it will only be able to solve, or it will only be able to provide best fit linear regression, etc. But we want neural networks to perform one step better. So if we, for example, take a look at this classification problem over here, without any activation function, it will just try to give the best fit line which separates as many blue and red data points as much as possible. But ideally, we want something that understands this environment better and creates a much better boundary, which is most of the time non-linear. So to introduce this non-linearity, we add some activation functions. So let's kind of look at the typical toolkit of activation functions that are used in neural networks, and also where they are used within the neural network. So if we look at this broad outline of a neural network, the input layer is not going to have any activation because the input layer is the raw data, and you don't want to have any activation function act on it directly before it's fed into the neural network, right? Because that's information directly coming from your experiment or system, so we don't want that to be tampered with. In the hidden layers, we typically use a bunch of functions like this sigmoid, tanh or hyperbolic tan, or ReLU, which is rectified linear unit, leaky ReLU, max out, etc. The purpose of these is to again introduce nonlinearity. We'll be going more into detail of when to use these and their advantages, disadvantages later. And in the output layer, typically for regression problems, there's no activation because the resultant number you're getting is the estimate your neural network is providing. So you don't want to make an activation function act on that. Whereas for classification, you might need to use a softmax function because you need it to be like a probability and the values have to be between 0 and 1. This also will be discussed more later on. Now we'll be going into cost functions, which will be explained by Kishore.
All right. So till this point, if you have any doubts, you can ask. You can also ask in chat. Are there any doubts? Okay, cool. Let's move on. So, yeah, moving on. Let's look at cost function. What is a cost function? So, we use machine learning models to predict some values, or we sometimes we can even use it to classify something, like classifying images, or like many other purposes. But in all of these cases, we need to evaluate our prediction. So we need to know how good our predicted or estimated values are compared to the true value. So to do that, we use something called the cost function, which is just to see how good our predicted values are. And in machine learning, especially in supervised learning, we have two types of problems. So the first one is the regression problem, and the second one is classification problem. And for both of these, we have different types of cost functions. And so let's look at them one by one. So in the case of regression, we have three cost functions, three types of functions, and they are mean error, mean square loss, and mean absolute loss. So going to mean error, and before that, yeah. So in the upcoming slides, I will explain those three cost functions, and in each one of them, I will mention something called as error, and this is what I mean when I say error in those cost functions. And this is nothing but the difference between the actual value and the predicted value. So suppose let's take this example. This is a linear regression, and according to this plot, the predicted value is somewhere here, somewhere where my mouse is pointing, and the predicted value is here. So the error will be the difference between these two values. Okay, so let's look at mean error. Okay, so now we in forward propagation we input data, and then we get some output at the end of the neural network. So now what can you use as a cost function? So the first thing, the most intuitive thing that comes to our mind is the mean error. So let's just calculate the errors for each data set and then take the average. So that's the most intuitive thing that comes to our mind. Well, yeah, this is a simple cost function, but then there is a catch. I mean, there's a problem with this cost function. Why? Because so suppose let's say some errors are negative and some are positive, and suppose let's take an example where they cancel out exactly. In that case, our cost function, the value of our cost function will be 0. And what does it mean? It means we have perfectly fitted the line onto the data set. So which means we have fitted each and every data point in the line. So which is obviously wrong. So for example, so say we have 100 data points here, and 50 of them are above this line and 50 of them are below this line, in such a way that the cost function is 0. That is like the sum of the difference in distances, they cancel out exactly. So that means we are fitting this line perfectly with the dots, which is obviously wrong because some of them are above this line and some of them are below this line. So this cannot be used as suitable cost function. But here's how we calculate it anyways. So we first for each data set we find the error, just actual minus predicted value, and then we sum it up and take average. Okay, so moving on. Next we have mean absolute error. Okay, so the problem with mean error was that there are negative values, right? So how do we eliminate them? So the one thing that we can do is take the modulus of all the errors, and that will work. And that is exactly what we do here in mean absolute error, and it is also called L1 loss. So how do we do that? We first find the error and then we take the absolute values, then we sum it up and take average. And this is the mean absolute error cost function. Uh, but one problem with this is that this is not a very good differentiable function. As you have studied earlier, modulus functions have non-differentiable points. So they have sharp points where uh, the functions are not differentiable. And our main aim in neural networks is to minimize the cost function so that we fit the data perfectly. And how do we do that, which we'll look at it later. But one thing that we will do in that process is we take the derivative of these cost functions. And taking the derivative, it's not easy to find the derivative of these functions because sometimes they are positive, sometimes they're negative if you remove them all. So this is not the most commonly used cost function because of this problem, but still it is used with some other complex algorithms, some algorithms that we can use to minimize this function. So what is the other way to overcome that negative error? The other thing that we can do is to square them and take average, and this works perfectly. Why? Because this is a perfectly differentiable function. We know the differential of x square is 2x. So in that way, yeah, we can see this is a very good differentiable function. And yeah, this is the most commonly used function for regression problems. How do we calculate it? We just take the difference and square them up, sum it up, and then we take the average. And this is called L2 loss. And yeah, this is the mean square error cost function. And this L2 loss also has a disadvantage. So suppose, let's take this example. Um, so suppose say we have an outlier here. So an outlier is something, it's a point that is very far away from the rest of the points, from the majority of the points. So say, okay, these are some data points. Let's say we have 1,000 data points. Let's say just one data point, let's take a point here that is very far away from the remaining points. So we call that an outlier. Uh, so how does it affect MSE loss? So we know that we take the square of the errors in the cost function, right? So this distance is obviously large. The distance between outlier and this line is very large. So consequently, the value of the cost function will also be very high. Which means, so when we try to minimize the error, this line has to be inclined towards the outlier so that we can reach the minimum of the cost function. In which case, the line will become something like this. So like you can see the motion of my mouse. So the point is here. Just to fit this point, this line will be inclined towards that point. So which means we'll obviously lose the accuracy because just for a single point in 1,000 data points, we are inclining the straight line. So which is obviously not good because our accuracy goes in rapid, becomes very less. So, but if you don't have any outliers in a data set, yeah, then L2 loss is perfectly uh, fine. But if you have outliers, yeah, L2 loss can be a problem. And how do you use L2 loss in that case? We can first remove outliers from the data set, or we can go for L1 loss. But in case of L1 loss, we need to use some complex algorithms. So this is about cost functions for regression problems. And this is a graph. So you can see in case of mean absolute error, we have a sharp point. This is a non-differentiable point. And this is a smooth curve. This is a MSE loss. So yeah, and this is called something called gradient descent, which you'll learn later in the session. Okay, and that's all for regression loss functions. Now coming to classification loss function. Classification is a bit different from regression. In classification, let's take image classification. So we feed in an image, and then we want to find out whether that image belongs to the cat class or a dog class. So in that way, here the thing is, unlike in regression cases, we don't have some continuous output. So we have only discrete output. So it can either belong to the cat class or not. But in regression cases, we predict some number and we get some continuous numbers. So that's why we cannot use the other functions. Uh, and there are many loss functions that are used for classification. But the one that's mostly used is cross entropy. And cross entropy, this formula is something similar to what you read in thermodynamics. So this will be the formula is nothing but minus of in brackets we have y1 times log of y1 dash plus y2 times log of y2 dash plus y3 times and so on. What are these y1 and y1 dash and so on? So y1 is the actual probability that the image belongs to that particular class. So let's say y1 is for the cat class, y2 is for the dog class, and y3 is for the horse class. Uh, Suppose the image that we feed in is a cat. What is the actual probability that the image belongs to the cat class? That will be 1, and rest all will be 0. Because the actual probability can either be 1 or 0, because it can either belong to a cat class or not. So there'll be 1 or zeros. Uh, y1 dash and y2 dash and y3 dash, they're all predicted probabilities. And these are the probabilities that we get as output from the neural network. The network can only predict which class it belongs to with some probabilities. And so we feed in these probabilities here. And why this minus sign? Well, probability always lies between 0 to 1, and logarithm of that will be negative. So, and to compensate for that negative sign, we put another minus sign here. And we can't use MSE loss for classification. And the reason we'll see, and we'll go deeper into this cross entropy in the next session, which will be on image classification. Okay, and next we have gradient descent, which will be explained by Ishan. Over to you, Ishan.
Yeah. Is the screen visible?
Yes, Ishan.
Yeah. Okay. So, hi guys, this is Ishan, and I'm going to explain a very important concept in machine learning, that is gradient descent. So, what is gradient descent actually? So, gradient descent is a technique that tells us how we can go towards the optimal solution. So, basically, in any neural network, we initially feed random values of weights and biases to the neural network, and eventually we go on minimizing the error and we reach the optimal solution. So gradient descent is just a technique that tells us how we can go towards the solution. So it tells us the way. So don't get scared by the paragraph.
I adore Einstein, and therefore I wrote these fancy paragraphs. So let's just focus on the figure here. So this is so initially we take some random point. So this is a graph of the cost function versus a parameter, that is we took it as weight. So this is the graph, and initially we took some point on the topmost left side, and we approached it in steps to the optimal solution. So the gradient descent has a formula through which we work on and we reach the solution. So what exactly is this formula and how it works? So let's take an example and see how does it work. Okay, so this is the example. Let's say we want to predict the height of a person based on his weight. So how can we do that? So let's say initially we have a data that says a person, let's say Ishan, with height 0.5 units, with weight 0.5 units, has a height 1.4 units. Skandan with weight 2.3 units has a height 1.9 units. And Kishore with weight 2.9 units has a height 3.2 units. So that is the data. We're just taking 3 points for simplicity. And we want a line that can predict these values with a good amount of accuracy. So how do we approach this? So let's take the mean squared error as it is as the simplest form of error we can take. So what exactly is this? Let's look at the first image, the topmost left image. So we first calculate the sum of squared residuals. So as Kishore had explained, the mean square error, we are just doing that. So that is the actual height, that is 1.4 minus the predicted height. And the predicted height we predicted through taking some random line initially. So the intercept is the variable, and initially we can assign any value to it. So let's say initially we assign some value 0 to it. Okay. So in the second figure on the right, we calculate the gradient. And let me first show you what the formula of this gradient is. I think you know this formula, but I'm just uh, reminding you of what it is. So the x on the left is the old parameter. Sorry, x on the left is the updated parameter. The x on the right is the old parameter. LR is the learning rate, and the df by dx is the derivative of the cost function with respect to the parameter x. So I'll just explain you what this learning rate is. It's a very simple thing. So the learning rate is basically the length of the steps that we are taking. So in this bottom right figure, you can see we are taking steps while reaching the optimal solution. So the learning rate is basically just the measure of the steps that we are taking. It can be big or small. So we'll see how this works through the example. Okay. So on the topmost right figure, what we are doing is we are just calculating the derivative df by dx. So from the left, with a minimal amount of knowledge of calculus, you can understand what we are doing. So here we calculated the derivative of the cost function with respect to the intercept, that is the variable here. And initially we took the any random value of intercept, we took it as 0 just for simplicity. And this, yeah, and we took the slope also as some random value, let's say 0.64, and we found the value of the cost function, that is minus 5.7. Sorry, it should be divided by 3, but let it be. You can understand. And so now coming to the step size, now we multiply this minus 5.7, that is the derivative or the gradient, with the learning rate. So the thing with the learning rate is it is the measure of the step. So if you take a very big step, you may just go from the left side of the curve to the right side of the curve, and you'll just miss the solution. It will obviously save time, but it will never lead you to the desired amount of accuracy. So now let's say we take small steps. So maybe eventually we'll reach the solution, but it will require a lot of time and a lot of efforts. So we don't want that either. So what we do is we keep we initially take big steps, and later on, as we reach the solution, we start taking small steps. So this is what is called as schedule. It is just a terminology. It just refers to that as we reach the optimal solution, we go on reducing the step size. That is the value of learning rate. So here in the bottom right figure, the 0.1 is the learning rate, and minus 5.7 into 0.1, that is minus 0.57, is the step size. Okay, so the new intercept is equal to the old intercept minus step size. So that is what we get as 0.57. Now, for the next thing, we just repeat these steps, and then we reached eventually we start reaching the optimal solution in small steps, and ultimately we reach the solution. So this is all we do in gradient descent. So yeah, so now we'll come to backpropagation algorithm, and Kishore will take over backpropagation algorithm.
Yeah. So I'll be explaining how backpropagation algorithm goes. So essentially, this is like a combination of whatever we've learned so far. So our aim is to kind of adjust these weights so that we try to minimize the cost function, and the neural network behaves like the map that we want it to behave. So in each iteration, we basically calculate the outputs by using forward propagation, and the cost or loss which we get as a result of that is like a feedback to us to allow us to find out how much we need to adjust the weights by in the next iteration. Right? And we keep this repeating this process until the either rate of change of error becomes too small that there's no use in continuously iterating, or the error crosses some threshold, which is our maximum allowed threshold. Or in some cases, the operation might not converge also. So to understand how to tune our network better, it's important to find out to understand the intricacies of backpropagation algorithm. So now I try to delve a little deeper into how backpropagation works. So, okay. So now if you can see my screen over here, you can see a marked neural network. And I've taken some 3 hidden layers from the middle, random 3 hidden layers, which are consecutive. And they are L plus 1, and L plus 2. So the important thing to realize about backpropagation is that it's a recursive algorithm. So the gradients calculated in the Lth layer depend on the L plus 1th layer and the L plus 2th layer, and so on. So we try to first get an idea of how it works somewhere in the middle. And then if we show that we can get the gradients of the last layer, then we can keep working in reverse to show that the gradients of all the layers before it can also be calculated. So now let's kind of understand how this works. So our target in this example will be this weight over here. So let's take this weight. So this is weight 1 to L. So if you remember the notation, Wij L refers to the weight going from the ith neuron in the Lth layer to the jth neuron in the L plus 1th layer. And L is the layer where the starting node is. So this will be the notation that I'll be using now. And this is the directed edge, which is coming from this node over here to the second node in the L plus 1th layer. So now our aim is to tune this weight. So the parameter which we need to calculate. So if suppose C was our cost function, we are interested in calculating dou C over dou W1 plus 2. So why are we doing this? Like, because we just studied in gradient descent. As Ishan said, we have to keep adjusting this our required number by small steps proportional to the gradient. So if we calculate this grad C vector, which will give us the direction of the steepest change. So if we move along the grad C vector, we'll have the maximum change. But we're interested in moving opposite to the grad C vector because we want to reduce the cost function as much as possible. And each time we adjust the weight vector by some quantity that is proportional to this gradient. So the new updated weight vector will be W minus some alpha times grad C, where alpha is the learning rate, which we just saw now. So, and remember, W is the entire vector of weight. So W would include all the weight starting from the first neuron of the first layer to the first neuron of the second layer, and so on. So W is this entire vector consisting of all the weights in the neural network. And when we are calculating this gradient, it's important to remember that cost is fundamentally a function of all the weights as well as the biases. So all the weights Wij, as well as the biases Bi. Right. So it's this with respect to these weights and biases, we have to try to minimize this cost function. And one more thing to keep which we need to remember over here is that every time we calculate the cost function, we don't always iterate through all the examples in the neural network. Sometimes we take training samples or batches to kind of reduce the cost of the time complexity of calculating the cost, because every time we need to calculate an output for a set of inputs, we have to go through the entire forward propagation process. So we sometimes take a sample of training data and calculate the cost with that, and then set the weights with respect to the gradients we get from that training batch. And we keep randomly shuffling and take different training batches and so on. So now let's get into the process of finding this gradient. So for this particular weight, the update will turn out to be W12L minus alpha times 2C over. So our target is to find this. So we can see that there's no direct way to kind of find this, because we don't know the exact function between C and W. It's multiple functions are stacked on top of each other. So we try to use chain rule over here. So to try to shift the dependency on W to make it depend on some other variable in the L plus 1 or L plus 2 layer, so that we can kind of get recursion over here somewhere. So now just using chain rule, my first target is to find out the variable in the L plus 1th layer, which depends on this weight W1 to L. So we can see that this particular weight is the edge connecting A1L to A2 L plus 1, which is the second node L plus 1th layer. So the weight that's connecting these two is our desired weight. So W is going to be directly influencing this particular node. And in fact, in the L plus 1th layer, this is the only node that it can influence. So all other variables that are affected by W1 to L all have to pass through this particular node A2 L plus 1. So we can take, using chain rule over here, we can split this as dou C over dou A2 L plus 1 times to A2 L plus 1 by W1 to L. Right? So if it's like hard to keep track of the notation, just try to remember the A's and the A, W, Z, etc. So okay, but we still haven't solved the problem over here, because we still don't know how to calculate this, and we've introduced a new term over here. But it's important to realize that we've passed on the dependency from layer L to layer L plus 1 by doing this. So if we could somehow get this, we have succeeded in getting a recursive algorithm. So this is actually easy to calculate, because we just saw in forward propagation how this weight would affect this particular neuron's value. So if you remember, sigma of Z is what gives you the neuron's output value, and where Z was the linear sum of the weights times neuron outputs of the previous layer. So we know that sigma of Z to L plus 1 is what gives us A to L plus 1. So we know that, and we in turn know that we know how W is related to Z, because Z is simply A1 times W1 to plus A2 times W22. So that relation we can get. So now let's split this derivative once more essentially. So earlier we had OC over O2 plus 1 times O2 plus 1. Now we're introducing this new term Z, so that's becoming times now this third derivative, which is going to be Z with respect to the weight which we are interested in. That would be. So now this is easy to calculate, and this is also easy to calculate. And okay, to see how that would be, we know that sigma of Z is what gives A, and these two are of the same layer, and they are for the same node, right? So if we take this derivative, it's simply going to be sigma dash of Z2L plus 1. It's just the derivative of sigma with respect to Z at that point. And this is easy to calculate because sigma is the activation function which we've set for the neural network, right? So we can, we already know what the derivative of sigma is going to be. And to calculate this, we need to look at the relation between Z and W, which we got originally in forward propagation. So looking at these two neurons and this weight, so this weight would, so remember these two neurons should be affecting this Z value. For a general neuron, it would be all the neurons on this layer, but we're just having two for now. So now taking the weighted sum of these two neurons with respect to these weights, we would get this Z2L plus 1 is equal to A1L times W12L plus A2L times W2L. So now this is the relation between Z and W, and this would help us to calculate the partial derivative with respect to W. So the important thing to remember here are that the W's are the independent variables. They don't depend on each other. Whereas the A's are the A variables were created from the W's. So when I take partial derivative with respect to W1 to L, this would completely get cancelled because this term is completely independent of W. Because when this node was calculated, A2L, it depended on the weights of the previous layer, L minus 1. So that this term would completely get cancelled. And when we're taking derivative with respect to W1 to L, we would just get A1L would be the only thing that we need. So this derivative would essentially become dou C over dou A2L plus 1. This remains. We still haven't figured out how to deal with this first term times the derivative of this activation function times the value of the. So the interesting thing that we need to observe are the second and the third terms. So the fact that these two terms are directly proportional to the partial derivative of the weight is something that we need to remember when we're designing neural networks. So going back and seeing what this implies. So we are saying that A1L is directly proportional to the partial derivative of the weight that starts from A1L. So this is something important that you want to remember. So if this neuron's value becomes really small, the magnitude becomes really small, it would start correspondingly affecting the weight of the weight that is connected from it. So this is something that would motivate us to design optimizers later on, because sometimes a small A value could force the update of the weight also to be small, even though that need not be how we want it to be. So that is one thing. And the second thing to notice is how the activation function is also affecting the derivative of the activation function is also affecting the rate of change of the weight. Because if we later when we see sigmoid functions, we'll be seeing that at certain points the derivative of the sigmoid function becomes rather flat. So that would as the derivative of the sigmoid function becomes 0, it would also kind of cut off this and make the derivative of this weight also very small, again making the neural network kind of saturate. So it is important to remember that this activation function's derivative as well as the node's value are directly influencing our weight. Now let's kind of focus on seeing how this derivative is being calculated. So we can go through it, go through the following process. Like for example, again, so let's try to use chain rule over here. So now we're interested in calculating the cost function's derivative with respect to the A value at this node. So dou C over dou A2L plus 1. So now let's similarly how we did for the weight, we'll try to identify the variables that depend on A2 L plus 1. So maybe redrawing this more cleanly over here. This is the L plus 1th layer, and we have two nodes in the L plus 2th layer. This node would directly affect these two nodes in the L plus 2th layer. All other nodes it affects would have to pass through these two nodes. So when we are writing the chain rule, we could split the dependency on the L plus 1th layer to the L plus 2th layer, which is how that's our motivation to make this a recursive algorithm. So we know these weights would be W21 L plus 1, and this would be W22 L plus 1. So we know that the Z value at this node, which is Z1 L plus 2, would directly depend on the A21 L plus 1, right? So remember that this is with respect to which we want to calculate the derivative. So we want to see how this value affects these two variables. So splitting again using chain rule, we can write this derivative rho c into A2 L plus 1 as rho c over to A1 L plus 2 times the derivative of A1 L plus 2 with respect to A2 L plus 2. So and similarly, now remember there are two branches which the derivative is passing through. So there's going to be another one for the second. That will be A2. So that will be rho A1 L plus 2 times rho C over rho A1 L plus 2 over A2 L plus 2 over rho A2 L plus 1. So essentially to reiterate what we're doing is we're calculating the partial derivative with respect to this node, and then we're taking the partial derivative of this node with respect to the node we are interested in. Right? So that's the flow in which we want to go through. And so that's how we got the split over here. And if we can also remember that there is the A2 L plus 1 is directly influencing the Z value at this node. And that is and when the sigma function acts on that particular Z value, it is creating the A values of the L plus 2th layer. So we have to split this once more in terms of the Z, because this A is directly affecting the Z and the Z is creating the A of the next layer. So splitting it once more, we would get partial derivative with respect to nodes of the L plus 2th layer, and then their respective derivatives with the Z values at those nodes. And then finally, the derivative of these Z values with respect to the variable with which we want to calculate the derivative. So, and of course, so if this was J, these would be I. And you would be summing this over all the I's of that layer. Right. So for this particular L plus 2 layer, there are only two nodes. So you would only have two terms in this. And now the important thing to realize is that we've essentially pushed the dependence of derivatives from the L plus 1th layer to the L plus 2th layer. So, and again, this dependence is easy to calculate because we know that the weight connecting AJ to ZI, which is JI L plus 1 times AJ L plus 1. This term is going to be there in the expression for Z. So when we take the partial derivative, it's only this that is going to remain. So this would turn out to be Ji L plus 1. So this is already calculated. This is again the derivative of the sigma function. And this is again now we shifted the dependency to the layer L plus 2. So this process is going to keep getting iteratively repeated. So we're going to shift these partial derivatives to depend on those on L plus 3, L plus 4, and so on. And if you go back, so remember what we just calculated now is just this value. So these two are already calculated beforehand, and we just calculated the partial derivative with respect to the node with the weight is ending at. So originally we started from this node to this node, and the starting node is directly proportional to the partial derivative, whereas the partial derivative of the ending node is directly proportional to the partial derivative. So this is what we need to take away from this. Like you don't have to remember all this notation, etc. But we should also realize that the partial derivative of this node is again dependent on the derivative of the activation function. So when you substitute this over here, the derivatives of these two activation functions are getting multiplied. So as you compound this over several layers, all these derivatives are going to get multiplied over a large amount of layers. So this again we'll see when we go over to the sigmoid function, how this will sometimes cause a really small gradient to happen, especially if the gradient of your sigmoid function or activation function is lesser than 1. When you multiply several of these gradients together as a result of the recursion, the resultant value will be very small. So we won't be able to make a substantial update to the weight. So that's it for how the back propagation algorithm works. So now using this as motivation, we'll see how certain we'll be going back to the certain activation functions and seeing how they work in a more intricate manner. So going back to the PPT. So this is what we just looked at, the entire back propagation algorithm. So we found a method to iteratively tune the weights in reverse order of layers. And again, yeah, I didn't mention how we would find for the first layer. So for the last layer, sorry. For the last layer, remember that the last layer is directly related to the cost function. So when we find the derivative of the cost function with respect to the output of the last layer, that is easily calculated. For example, if we had the square type L2 loss, it would be the predicted y minus the actual y, the whole square. So that derivative would be easily calculated. So just be 2 times their difference. And once we know that the derivative of the output layer, we can just work iteratively in reverse and get for all the other layers. So now I'm hoping you can see this slide with the activation functions. So over here, we are having a sigmoid function over here. So you can see the sigmoid function as well, its derivative being plotted over here. So the sigmoid function is 1 over 1 plus e power minus x. And the derivative, as you can see, kind of is maximum at 0 and tapers off both at extremes. So for this particular function, the derivative is 0.25 is the maximum value of the derivative. And then it tapers off to 0 in both directions. So using this as your activation function would satisfy the requirement of introducing non-linearity into the neural network. But at the same time, it has some disadvantages. First thing is saturation. So look at the fact that the derivative is becoming 0 at both extremes of the neural of the activation function. So as we saw before, the weight derivative is directly proportional to this. And we also saw that the activation function's derivative is continuously being multiplied over several layers. So if this becomes small, when you multiply over several layers, it's going to compound further. So the resultant for the layers which are closer to the input layer, their updates are going to be very small. So that's not good. That's going to cause a neural network to learn very slowly. And and another issue with this is the fact that it's not zero-centered. So why is that a problem? Since this is not zero-centered, remember that all the outputs of all the range of the sigmoid function is always positive. And we also see that the A values are directly proportional to the partial derivative of the weight. So when all these values are positive, it forces the partial derivative with the rate with the weights to be either all positive or all negative. That sign would be dependent on the partial derivative with the node of the next layer. But it would force all the weights of that particular layer to have the same sign of partial derivative, to be either all positive and all negative. But in some cases, that's not the direction in which grad C would be. So we wouldn't be updating in the most optimal direction. So that problem is solved by using this hyperbolic tangent function. You can see that by shifting it. So this tangent is basically a linear transformation of sigmoid function. You can see the relation over here. You basically like slightly squished it in the vertical direction and elongated it in the squished it in the horizontal direction and elongated it in the vertical direction and shifted it down by 1 unit downwards to remove that zero centering problem. And this tool, however, has the problem of vanishing gradients because it again tapers to zero gradient in the extremes. And the alternatives to this, to solve this problem, are the ReLU and leaky ReLU functions. So the ReLU, or the rectified linear unit, is basically, it looks very simple, and that's the reason why it's used also, because it's just zero when your input is negative, and x when your input is positive. So it looks like y is equal to x line on the right hand side, and it's a flat zero line on the left hand side. I mean, it's computationally efficient to use this because its derivative is very easy to calculate. It's constant, and you just have to look at the range of the input. And um, the one disadvantage of the function is that you're losing some information. For example, all negative values are being collapsed to zero, whereas sigmoid and tan H were both bijective functions. So all the reals had a unique output. So hello? Can you see the presentation?
Yeah.
Okay. Yeah. Okay. So yeah. So I lost some connection. Okay. So the ReLU and leaky ReLU have the advantage of having very fast. You can compute the derivatives very quickly, but the ReLU loses some information because it's compressing all the negative values to zero, and it also results in dead neurons because since the slope over here is zero, as we saw, the slope of the neuron directly affects the partial derivative of the weight. So when the partial derivative of the weight becomes zero, it won't get updated anymore. And if that happens to enough number of weights, then the back propagation to the layers, the more inner layers towards the input layers, their partial derivatives also won't get updated. Their weights also won't get updated, and that will stop your neural network from learning any further. So to solve that, you introduce a slight leak over here, a small slope on this side to kind of prevent the slope from on the negative side to become completely zero. And to get kind of an intuition of how ReLU introduces non-linearity, because ReLU seems like it looks linear on individually on both sides, but the fact that we use like an inequality to decide what the output is going to be introduces some non-linearity. So to get some, let's say we had just a two-dimensional function which we want a neural network to behave like. So let's just take sin x. Sin x has only one input, and we want to adjust this ReLU to behave like a piecewise linear approximation. So using the weights and biases, you can adjust you can move around this ReLU over your graph. So by adjusting the bias, I can kind of shift it up and down in the y axis, and by adjusting the weights, I can kind of shift the angle between the zero line and the greater than zero line. So I can adjust this angle as well as move this around, and that kind of gives me a flexibility to piecewise linear approximate any kind of function. Similarly, in 3D, if you want to think about this, any surface, any 3D surface, you can optimize, you can approximate using piecewise planes. So that's an intuition for how ReLU introduces non-linearity. So now moving on to some optimizers. So now we looked into the back propagation as well as the how the activation functions affect the back propagation. Now this would give us some reason as to so I was highlighting some earlier problems such as this vanishing gradient and dead neurons, etc. So this is why we need to introduce some optimizers to kind of prevent the weights from being updated by very small amounts. So
Skandan.
Yeah.
Maybe let's resume after a short break.
Okay.
I guess the previous topic is done. So maybe before we start with the next thing, we'll take break till 3:10.
Okay, sure.
Okay.
Yeah.
So we'll resume at 3:10, everyone. Ishan, I think you can start now. It's 3:10.
Yeah, okay. Is the screen visible?
Yeah, Ishan, go ahead.
Yeah, okay. So, hi guys, I hope you had your break. So, let's resume now. So, with all the knowledge of cost functions and backpropagation and an introduction to gradient descent, we'll have a look into the various methods in which gradient descent is used. So, coming to one of the most important things is the stochastic gradient descent or SGD. So, stochastic gradient descent is a method which is particularly used when the number of data points are large in number, or there are redundancies in the data set. Like in the following figures, you can see there are clusters of points. So these are redundancies. So now if we go and consider the normal gradient descent, we have to consider all the points, and that will create a lot of mess, because then we'll have to take into account a lot of derivative terms, and basically that would get a bit messy. So to avoid all that, uh, what we do is we take a single point from any one of the clusters, and we just go on with the normal gradient descent formula. We apply the normal gradient descent formula, and this is basically, this is also an example of linear regression, where we are trying to predict the values with the help of a line, the line curve. So basically, to find this line, initially we just take one point from any of the clusters, uh, and we go on with the gradient descent formula. So then we get some slope, and then we update the parameters. So with this slope, now we take some other point from some other cluster. So in the figure 2, you can see that we have took some point from the bottommost cluster, and then we again go on with the same steps of gradient descent, and then we calculate one more slope and one more intercept for that line, and thus we go on taking one point at a time from different set of clusters. And this is how we reduce the calculations in the gradient descent part, and we reach the optimal solution. So stochastic gradient descent is one such method, and there is one more method called as the mini batch gradient descent. So I would say that mini batch gradient descent takes the best from stochastic gradient descent as well as the normal batch gradient descent. So in the normal gradient descent, we take all the points at once, and in stochastic gradient descent, we just take one point at once. So in the case of, let's say, the redundancies like the clusters that we're having here, what we do is we take one point from each cluster. So now here we take 3 points, one point from each cluster, and we perform the set of operations that we do in gradient descent on these 3 points collectively. And all the steps of the gradient descent, updating the parameters, updating the slopes and intercept of the line, it goes on. And this is one more method by which we reach the optimal solution. So this method is basically faster than stochastic gradient descent, and it requires lesser efforts than the normal gradient descent method. So mini batch gradient descent is a very good method for optimization techniques. Okay. So apart from the gradient descent methods, there are certain methods like the adaptive learning methods. So if you remember, I had said that the learning rate should be changed accordingly as we reach the solution. Because with big steps, we might overshoot and we might just reach the other end of the curve. And with small steps, we'll reach the solution, but it will require a lot of time. So adaptive learning methods, as the name suggests, adapt to suitable changes during every iteration. That every iteration is called an epoch. It's just a terminology for the iterations. So we have various adaptive learning methods in machine learning, such as AdaGrad, RMSProp, ADAM, etc. And basically, these methods modify the value of the learning rate during each epoch. So how do they do that? What is the mathematics behind it? We will come to it in a few seconds. So now we'll see how these AdaGrad, RMSProp, and ADAM work. So passing on to you, Skandan.
Yeah. So So, okay, the first optimizer we'll be discussing is the AdaGrad optimizer. So we were saying that certain problems are occurring such that, like for example, the gradients as we went back propagated, the gradients sometimes vanish because sometimes if the gradients have small values, they get compounded across several layers and they vanish. Or sometimes you have certain sparse parameters whose input values due to the raw data that you get, the input values themselves could be small for certain reasons. And we know that the neuron output directly affects the weight of the corresponding edge that's connected to the neuron of the next layer. So sometimes small inputs can also, smaller sparse inputs can also lead to very small gradients with respect to the loss function. So when you have sometimes an uneven set of gradients like this, certain gradients which are much smaller than others, but it can sometimes lead to a divergence in the values of the weights. Some weights might get updated by very, very large amounts, whereas other weights are getting updated by very small amounts. So this could prevent the neural network from, this could cause the neural network to diverge very quickly. So you want some kind of mechanism to control this. So that's taken in, that's solved by the AdaGrad optimizer. So here you have an adapted learning rate. So ADA stands for adaptive. So the learning rate adapts to the gradients of the previous iterations. So if a particular weight has been consistently getting very, very small gradients, the learning rate looks at that and kind of makes itself larger. So a larger learning rate becomes comparatively larger for those weights which have had smaller gradients in the previous iterations, and it becomes smaller for those weights which have had consistently getting large gradients in the previous iterations. So it kind of balances out and somewhat evens the difference between weights which are having a large difference in their gradients. So mathematically, how this is done is that the derivative of the loss with respect to the weight which we are considering over all the previous iterations, the square of this value is taken and summed. So we're squaring because we're concerned only with the magnitude, and we're summing this over all the iterations using current and before. We're summing over all the iterations to kind of get an accumulated history of how much the general value of this gradient has been. So if this number is large, notice that this is what is coming under alpha. So alpha is what is having the accumulated history of the gradients. And if this alpha becomes large, that means that this weight has been consistently getting larger and larger gradients over time. This learning parameter is inversely proportional to the history. So if this becomes very large, the learning rate decreases, and you introduce a small constant epsilon to prevent to avoid divisibility by zero. For example, in the first few iterations, it may turn out that this dou L by dou W might be zero. So to avoid complications because of that, you introduce a small number epsilon to solve this problem. And there is a particular disadvantage to this, the fact that over as iterations keep increasing over time, when you have a very large number of iterations, this alpha will get very large because you're continuously adding positive numbers to it, and the learning rate will decrease. So the overall learning rate, if you can take like the average learning rate over all the weights, it will decrease, but it would still be satisfying its original function, which is kind of to balance the relative values of the learning rate between weights which are having large gradients and small gradients. So that problem is solved, but it introduces this new problem of having of getting very small learning rates after a large number of iterations. So the other optimizers that you will be seeing work on solving this problem. So over to Kishore, who will be explaining exponentially weighted and moving averages.
All right. So next, we'll look at something called exponentially weighted moving averages. Before that, if you have any doubts, you can ask, or you can put it in the chat also. Are there any doubts? Okay, cool. Moving on. So next, let's look at something called the exponential weighted moving averages. This is not an optimization algorithm. This is just a different kind of average. We have seen normal averages, which is just summing up and then dividing by the number of data points. And then we have weighted averages. We know weighted averages. We just multiply by some weights, and then we take average. But this is different. So this is exponentially weighted moving averages, and we'll use this to understand the upcoming algorithm, optimization algorithms. Okay, so consider this graph here. So forget about this red plot for now. So we see we have blue dots here. So say there are some 1,000 blue dots, and the exponentially weighted moving average will be given by this formula. So that is nothing but Vt equals beta times t minus 1 plus 1 minus beta times st. Beta, and where beta lies in the range of 0 to 1. And so I'll explain this formula. This is not intuitive at first, so I'll bring some intuition into it. Before that, so we'll see what Vt and St means. So Vt is the tth average, and St is the current value. So for instance, let's take some data points, say the 100th data point here, somewhere here, and the exponentially weighted moving average of that. So yeah, so this will be S100, right? This data point. So V100 will be, which is nothing but the 100th average. That will be 1 minus beta times this one ST, which is S100, plus, and then we have some other, we consider the previous point also. It's say S99. Yeah, the previous point will be S99. So that will have some other weight. And then we consider the point before that, S98, that will have another weight, and so on. So basically, the general form will be some weight times the current value, and some other weight times the one before that, and some other weight times the one before that, and so on. So for V100 will be some weight times S100 plus some weight times S99 plus some weight times S98, and so on till some weight times S0. And we'll now look at what these weights are. And to intuitively understand this expression, so we will have to expand this expression recursively. So I have written this expression for t minus 1 also. So for t minus 1, the formula will be v of t minus 1 equals beta times vt minus 2 plus 1 minus beta times st minus 1. And same for t minus 2 also. So there'll be Vt minus 2 equals beta times Vt minus 3 plus 1 minus beta times St minus 2. And we substitute recursively. So in place of Vt minus 2, substitute this one. In place of Vt minus 1, substitute this expression. And we get this. On simplifying, we finally get this expression. And this is what we are interested in right now. This is the formula, main formula. But this is the one that we can understand very clearly. And this is the one that's more intuitive. So if you look at this, what this says. So this is the teeth average, and here the ST is the current value, and that has the weight of 1 minus beta. And then the next data point, that is ST minus 1, that has the weight of beta times 1 minus beta. And the next, the previous point, which is ST minus 2, has the weight of beta square times 1 minus beta. And then we'll have the one before that, which is ST minus 3, that will have a weight of beta cube times 1 minus beta. So again, coming back to this graph, so again, let's take 100th average. We take 100th average, so that will be V100. So that will be 1 minus beta times S100 plus beta into 1 minus beta times S99. And then the plus, we take the next, the previous term, which is beta square times 1 minus beta times S98. Then beta cube times 1 minus beta times S97, and so on. So you get the idea, right? So basically, the weights are in GP. So that is the only thing to note here. The formula will be ST with some weight, and then plus ST minus 1 with the next term in the geometric progression, plus ST minus 2, and so on. So this is the formula for exponentially weighted moving average. And we'll use this to understand the following algorithms. So I hope this is clear. You don't have to memorize this formula, but this will be helpful in understanding how the optimizers work. Okay, so let's come to momentum. This is a very cool concept. This has nice, you'll get some nice intuition for this topic. So let's take this loss function. So some complex loss function. Let's say the 3D plot. So this is the 3D plot of that function. And for now, forget about the terminologies. Pathological curvature, just forget it. Just look at this graph. And this loss function depends on, assume it depends only on two parameters, W1 and W2, which are some weights of the neural network. And focus on this part of the graph. This looks like this part looks like a hill, and this one looks like a valley. So if I just magnify the image here, you'll see something like this. So this is one hill, this is another hill, and in between you have a valley. And yeah, this is the loss function. And we have two axes, W2 and W1. And okay, what do we do in gradient descent now? In gradient descent, we take a random point, and then we move in the direction opposite to the gradient vector to reach the minima. But here's the problem. So suppose if I start here and assume this as a trajectory of a very bouncy ball. So suppose if I stand at this top of at this point and then throw a very bouncy ball at a very high velocity in this direction, it's gonna keep bouncing between the hills or the walls, and then and suppose say our minima is somewhere in the valley, somewhere down the valley, and we want to go to the valley. But then in the case of gradient descent, it's like a bouncy ball that keeps on bouncing between the hills. So it never comes down to the valley, it never reaches the minima. So that's a problem here. And to solve the problem, we use something called momentum. And how do you solve it? We'll see. So again, this is another picture. In the case of gradient descent, we always follow the path. We always go in the direction opposite to the gradient vector. and say this is the direction, and this has two components, right? So this one uh, is points along the W2 and this one points along W1, because the gradient vector is a vector with partial derivatives as the components, and so this one points along W2 and this one along W1, and the yeah, so this is the trajectory taken by the SGD, and we want to go through the valley to reach the minimum. We don't want to bounce off the hills. So to do that, we use momentum, and this is the formula. Uh, this is what we just saw in the previous slide. This is nothing but the exponentially weighted moving average. So we take the exponentially weighted moving averages of the gradient at all these points. So whatever points we encounter, we take a note of it, and then we find the exponentially weighted moving average of those points. And then in regular gradient descent, we subtract the alpha times, that is the learning rate times the gradient at that point. But here, instead of gradient, we use the exponentially weighted moving average of those gradients. So that is the only difference between the traditional SGD and momentum. So in the case of momentum, we just use exponentially weighted moving average instead of the normal gradient. And why does this work? Like, how does this prevent the bouncing thing? So see that. So yeah. So to understand this analogy, so I'll explain. To understand this part, I'll explain with an analogy. Uh, let's take a ball again, so a bouncy ball. So suppose if I throw it from this point with a very high velocity, it's gonna keep bouncing off these walls and it won't reach the minima at the valley. So what we can do is, suppose if I give a very lesser velocity, it's gonna hit somewhere else down, right? So it'll try to go to the valley, and if we give very less velocity along this direction, that is this W1 direction, it can reach the valley easily. Yeah, so that's the idea here. So our aim is to somehow decrease uh, the component of I'll call it velocity. So the velocity along the W1 direction, so that we can reach the uh, minima easily instead of bouncing off these walls. So uh, how do you and how does momentum achieve this? So basically, you can see here we are taking the exponentially weighted moving average. And what is exponentially weighted moving average? It's just a sum with sum of the gradients with some weights allotted to them, multiplied by some weights. So yeah, so basically we take the sum. Uh, Yeah, so we take the sum, and suppose if we sum up the components of the gradient along W1 using the exponentially weighted moving average formula, we can see that like all these vectors are pointing opposite to each other. So they're going to have some cancellation effect, which will reduce the velocity in the direction of W1. And you can also see in the direction of W2, they point in the same direction. So they're going to have a reinforcement effect. Uh, and here, in case of the component along W1, it may not cancel out exactly, but yes, to some extent, it will cancel out. And so the bouncing effect is minimized, and you will have more straight velocity here because this component is reinforced. So that is the basic principle behind momentum, and that's how it works. So is that clear? Are there any doubts? Uh, yeah, this is just a picture. So without momentum, we'll have large amplitude in this direction. So it's gonna keep bouncing off and it will never reach minima. And with momentum, it can reach minima easily because we don't have much bouncing along this direction. So next we'll look at RMS prop, and RMS prop is very similar to Alagrad. So let's look at Alagrad now. So you see formula. So Alagrad, the formula for Alagrad is WT equals WT minus 1 minus this eta by root over alpha t plus epsilon times the gradient. This we use the same formula, almost the same formula, with a slight change. And there you saw the st here, in this case, this expression. Instead of vt, there in Alagrad you saw st. And that is the only difference between RMS prop and Alagrad. Sorry. Yeah, that is the only difference between RMS prop and Alagrad. And why do we have to define, create something like this? Because, well, Alagrad has a problem. So in Alagrad, as we move towards the minima, we're going to keep accumulating the sum of the squared gradients in the denominator. So in Alagrad, yeah, you can see this alpha t is nothing but the sum of the squared gradients. So we just keep adding the sum of the squared gradients and we put them in the denominator. And that's gonna decrease the value of this eta dash t, because the denominator, if the denominator is very large, then yeah, eta dash t will be very less. So which in turn will significantly lower the learning rate as we move towards the minimum. So that's the problem with Alagrad. And how does RMS prop solves it? Well, RMS prop, instead of the sum of the squared gradients, we take the exponentially weighted moving average of the squared gradients. And that's the only difference. And you can see clearly here, beta is lies between 0 and 1. So obviously, Vt, which is the exponentially weighted moving average, will be less than 1 because all these terms beta, this expression value will be less than the actual sum, that is st plus st minus 1 plus st minus 2. Why? Because beta square and beta lies between 0 and 1, so beta square will obviously be less than 1, and 1 minus beta will also be less than 1, and and we are multiplying all these values with a number less than 1, so obviously this expression will be less than st plus st minus 1 plus st minus 2. So yes, in this case, this expression will be less than the actual sum of the squared gradient. Hence, this denominator will be larger than the one that we use in Alagrad. So here we just take the sum of the squared gradients, and so this denominator will be larger. Smaller. Sorry. Yeah, this denominator will be smaller, and so our learning rate will be higher, which means we can reach the minima faster than Alagrad, and that's RMS prop. And next we have ADA delta, and ADA delta is another improvement for Alagrad, and there's only a slight difference between RMS prop and Alagrad again. And if you see RMS prop and Alagrad, we have one parameter which is alpha, and even in Alagrad we have this eta parameter. And so these parameters are called hyperparameters, which has to be defined by the user, the one who is training the network with before starting the training. So we have to define it manually. But in the case of ADA delta, we don't have to do anything like that. The algorithm itself will take care of the parameter. And how does it work? So we first find the something called the delta. And delta is the difference between the the current weight minus the previous weight. And mm, uh, yeah, sorry, this is not delta. This is delta. This is just the change in weight. Yeah, and this is delta, and this is nothing but the exponentially weighted moving average of the change in weight. Yeah, and then we also calculate VT, which is the exponentially weighted moving average of sum of the squared gradients. This step is same as the one that we did in RMS prop, and the update equation will be slightly different. Instead of that eta parameter that we used in Adagrad and RMS prop, here we'll use root over d of t minus 1 plus epsilon. And so here you can see we are not defining any external parameter that has to be defined before training the network. And once again here this epsilon is just small value, very small value, just in case this VT reaches 0. I mean, if it becomes 0, this uh, whole term will explode to infinity. Yeah, that is that is ala delta. And yeah, so here are some cool animations. So you can see the one that's red in color is SGD, and you can see it's going very slowly, and while the other algorithms are reaching the minima uh, faster than SGD. And here in this case, the star is the minimum. And that's about these optimizers. And now Ishan will explain some more optimizers in detail. Over to you, Ishan.
Yeah. Yeah. Okay. So the next method that we are going to study is called conjugate gradient method. So this is another method that makes use of gradients. And also there are some methods that don't make use of gradients, yet they reach the optimal solution. So we are also going to study some of these methods that are called gradient-free methods. So as of now, let's have a look at what conjugate gradient method is. So it is one of the most beautiful applications of mathematics and machine learning. So on the topmost in the topmost right figure, you can see a pathway that's highlighted with red color, and there is a path that is highlighted with green color. So if you can see, the red path is having is a much lengthier part than the green part. The green path seems to be a much better path than the red part because it reaches in minimum number of steps, and of course it takes big steps, so it reaches in minimum amount of time, and that is all what we need to reach the optimal solution. So the red part is how we reach the optimal solution by the normal gradient descent methods. And this green part is how we reach with the use of conjugate gradient method. So this conjugate gradient method makes use of conjugate matrices, and it basically determines the direction and the steps that we are supposed to take to reach the solution. So without the mathematics, this might seem something very abstract, but the mathematics is a very complex thing. And so I think I won't go into it as of now. But if you're curious to know about it, you can surely go and search for it. I'll attach a link on the group about this mathematics. So in this method, as I said, uh, in the normal gradient descent thing, the direction and the steps that we choose are basically random. So they might require a lot of time and efforts to reach the optimal solution. But here, with the help of the mathematics, we uniquely determine these directions and the length of the steps such that we reach the optimal solution in minimum steps and minimum amount of time. Okay, so this was the conjugate gradient method. I hope you understood it approximately, like the concept. Uh, so I'll move on to the next thing. That is the gradient free methods. This is what I was talking about. So as of now, the methods that we saw involved gradients in some or the other form. But there are also some methods that don't make use of gradients and yet they reach the optimal solution. So
Sir,
yeah.
sir, which is the best one, sir? Gradient or gradient free, and what is mostly used?
Mostly, I guess the gradient methods are used because I'll come to that because the gradient free methods require a lot of efforts and time. But in some cases where the gradient is difficult to find, or it is discontinuous, or it is discrete, or the function is noisy, in those cases we can make use of these gradient free methods. But mostly, the gradient involving methods would be good.
Okay, thank you.
Yeah. Okay. Okay, so these methods can be used, as I said, for problems where you have discrete functions or discontinuous functions or noisy functions. So the types of gradient-free methods are exhaustive search, genetic algorithm, particle swarm, simulated annealing, and Nelder-Mead. Like these are some of the examples of gradient-free methods. So these methods, as I said, cannot be applied on large scale data sets, like where you have a large number of data points. So in most of the cases, we have a very huge number of data points. So as I marked out, the gradient involving methods are more common. So, but we'll still look at these gradient-free methods. We'll have a look at one or two of these methods and get an idea of how these methods work. So actually the mathematics and the functioning of these methods is much complex than what it is in this course. So we'll not go into the mathematics and implementation of these methods. But again, if you're curious about knowing it, you can obviously go and search on the net. So let's look at one or two methods. So the first is the exhaustive search. So exhaustive search is basically like we tap onto every point on the curve and we check whether it's the solution. So that's the most basic thing, and that's a very stupid thing, I think, because tapping onto each point and checking whether it's a solution is a total waste of time and energy. So, but still, that is a method, and that comes under gradient-free methods. So this was all about exhaustive search, and it's obviously not used. So the second is genetic algorithm. So basically, genetic algorithm is a method that has been inspired from nature, how the genetic evolution works. So I'm not scaring you with biological terms. I'm just telling you how from where it is inspired. So what happens is that in what we saw in gradient-free methods, uh, we every time we ran an epoch, we found just one solution and we worked on it. So what happens in these methods is that uh, we don't generate just one solution, we generate many solutions in the start. So these solutions are called as population, which are initially generated. So population is just a terminology used for this initial set of solutions. So the most popular technique for initialization is the use of random binary strings. So I won't be going in what this is. As I said, that the mathematics and the functioning of these methods is very complex, but we'll just have a look of how these things works with suitable examples and graphs. So what happens is that initially we choose, let's say we have in the figure, we have chosen 5 solutions, that is 5 points, and we assign a score to every individual point with the help of a function called a fitness function, and the score is basically called a fitness score. So this fitness score determines the probability of that point to be chosen for reproduction. And also it tells us how better it is than the other solutions. So the score is the measure of these things. And so higher the fitness score, the higher are the chances of being chosen for reproduction. So in the next steps, what we do is we allow these points to reproduce in pairs of 2. And every batch that gets reproduced is called a generation. And these generations have scores and properties that are better than the previous generation. So this is, and what happens is that with every generation coming, we have better and better scores for every individual. And at the end, we attain an individual that has the best score, that is full score. So that individual with full score is the solution of our problem. So I'll show you with an example. So let's take f of xy is equal to x cube plus 15x square plus y cube plus 15y square. So let's say this f of xy is the cost function and x and y are the parameters, like say weights and biases. So initially in the first graph, you can see small points dispersed randomly. So this is the initial population that we take, that is the probable solutions. And later on, as they reproduce, these points start gathering towards the minima. So here, as you can see, it is very evident that the minima is 0, comma 0. So these points start coming closer and closer towards the minima with every generation, and eventually they become a point. So this is how we determine the minima in these methods. So you might be having doubts how this happens, and as I'm seeing again and again, there is quite a biological analogy and some mathematics that is involved. So we won't be teaching that here, but obviously you can go and search for it on the net. So this was genetic algorithm. And one more method that will look that is a bit similar to genetic algorithm is called particle swarm. So similar to genetic algorithm, initially collect a set of possible solutions. So in genetic algorithm, it was called a population. Here it is called the swarm. And what happens is that we assign uh, a certain velocity and direction to these points. And in what direction and what velocity they will travel depends upon the best solution that an individual point has found and the best solution that the whole swarm has found. So intuitively speaking, what this means is that the direction of the best solution determined by the swarm, it directs the whole swarm towards the best solution. That is the whole group of points. It directs the whole group of points towards the optimal solution. And whereas the best solution found by the individual point, it leads that individual points towards the optimal solution. So because we want both the swarm, that is a group, and every individual point to travel towards the optimal solution, both of these points are equally important. So again, with the help of some images, we'll look how this happens. So again, we'll consider the previous function as the cost function and x and y as the variables. So initially, you can see some small blue dots dispersed on the graph. And again, we know the minima, it is 0, comma 0. And as like this method particularly takes some more time than what genetic algorithm takes, because the velocity, because there are two factors that are involved. That is the velocity of individual point, that is the velocity towards the best solution found by individual point, and the velocity of the best solution found by the swarm. So this method particularly takes more time than genetic algorithm, but it still leads to a good accuracy. And as you can see, eventually the points converge towards the minima, and at the final stage, they merge into one point. So this is called particle swarm. So basically, there is these are the two methods that we saw. More or less, the other methods are also the same. These two methods just were to show or give you an idea how things work without the gradient. So this was it. And the next is zeroth order optimization. So the zeroth order optimization, I'm just going to the motive of this introduction was to just give an idea that a method such as zeroth order optimization exists. So as far as my knowledge is concerned, zeroth order optimization is a very recent and a very powerful method of optimization, and it is being used by leading data scientists and leading data science firms in the recent times. So the functioning of this method is extremely complex and mathematical and is beyond our understanding as of now. But this slide was just to give you an idea that something like zeroth order optimization exists. So as you guys will continue your studies and interests in AI and machine learning, at some point in your careers, you might be working on this zeroth order optimization. So this was it. Yeah.
Should we have a break now, or should we move on to the implementation?
Yeah, maybe we'll take a break till 4
Okay.
and take up. Yes, Kannan, I think you can start now. Skandan, am I audible?
Should I start?
Yeah, start please.
Okay. So, can you see the? Can you guys see the node?
No, it's not yet visible.
Okay. What about now?
It's still not visible.
Or else, do they have the link to the notebook?
No, it's still not visible. Maybe you can try sharing it again.
Okay. But okay, but does everyone have the link to the notebook? Like maybe they can just individually open on the.
No, no, no. You should share it on the groups. Please do that then.
Okay.
Share it on the WhatsApp groups.
Okay. Send it. So you guys can open the notebook. If anyone is unable to do so, let me know. I'll try sharing it again. Yes. Is it coming now?
No, it's still not visible.
It's weird. Okay. Is everyone able to open the notebooks on their computers in their?
Maybe Kishore or Ishan can share the screen.
Yeah. Okay.
Yeah, I'll share my screen. So, can you see my screen, right?
No, not yet.
Is it visible?
I'm not able to see.
Yeah, it's visible. Okay, Kishore's screen is visible. Maybe Skandan, you can just talk and then we'll see.
Okay,
how it goes
yeah.
then.
Yeah, okay, fine. I'll okay, I can see it now. So yeah, so first in this first part of the notebook, we'll be going through just a single perceptron, which is like a fundamental unit of the neural network. So this is basically equivalent to a neuron with a step function as its activation function. So you can play with this more and try to build using this is like a basic building block, and you can like combine these to make larger and larger neural networks. So first we're importing the necessary modules, and then we want to define the perceptron class. It helps to generalize this so that it's useful during implementing in declaring it multiple times when building a larger network. So first, we initialize the weights. The weights is an empty set, and after we then we define a fit function in this class. the fit function takes in the parameters, which is the x, which is the training input data, and y, which is the set of output data, which we'll use to compare data with for calculating loss, etc. And then finally, we have a learning rate and number of iterations. This can, when you declare the fit function, you can change these to other values also if you want to. And so once we get in the X data, we define the weights to have the number of rows that the input data and the number of features that the input data has, because we know that when the weight matrix should be multiplied with the X matrix in each layer of forward propagation. So we need to define the dimensions accordingly so that the matrix multiplication will be valid. And then we randomly initialize the weights. So all the weights will have random values initially, and we have one extra. We add one extra row because we need one extra row for the bias values also. So in this, because this is a perceptron, the weights are just going to be, it's going to be just a weight vector, because we're going to have one node and all the weights are going to come into that. So there's going to be a weight vector, and you're going to add one more row to that because the last row is going to be the bias for that. And then we go on into defining the for loop, which is going to go through for different iterations of training. So so this is going to behave like stochastic gradient descent. So we're just going to take one sample at a time while doing this, because we're going to take it for like a small set of points. And this perceptron is going to now behave like a classifier. So first we choose a random row from the input data. So you define that you just take a random integer from the possible indices of the input data, and then you take the corresponding row of that in the input. Then there's a self.predict function. The predict function is defined below, which will come to that. The predict is basically the forward propagation. So you put in the data from the various features in that row into your perceptron, and the error which we define is going to be the difference between the predicted value and the actual value, and then later we can square this to get the square error loss, etc. So, and the gradient descent step which we take is going to be the weights plus the learning rate times the error times the actual load value. Because if you remember what we saw in the back propagation step, that the derivative of cost with respect to the weight involved a derivative of the cost with respect to the neuron that the weight is connected to times the derivative of the activation function times the weight which we are multiplying with. So this substituting that into the update function, we can see that we multiply the learning rate times the error times the input parameter. And this, if you try to visualize this in terms of linearly separable data, every time this classifies a particular data point wrongly, the normal vector of the plane or line, whatever which is classifying, is going to orient itself slightly more towards the data point which is wrongly classified. So to try to include it within its the right side of the plane. And then below that, every 500 iterations, we try to give some sort of output to make sure that everything is going fine. So first, this is just for creating a graph for visualization. So there are two features that will two input features. We'll try to draw a graph and show you the how the line gets oriented better each time. And if you go down below, you can see that we define the total error and we keep updating the error square, the squared error each time to this total error. Can you scroll down slightly? Yeah, so every iteration we update the squared error to this total error, and then every 500 iterations we print the mean error. And below that, we define the predict function, which is basically the forward propagation which we used earlier. For a single neuron, this is basically just the dot product with the weights and summing the bias with this. So basically, for the bias, you can initially I just add the bias initially to the starting value. The activation is basically going to be the total number of the it's going to be the total sum, the weighted sum is going to be stored in this variable called activation. And then first I just initially put the bias, and then I add the dot product of the weight with various features. And then we know the step function is going to be the activation function. So if that is greater than equal to 0, it's going to return 1, or else it's going to return 0. So basically this perceptron, we can use it as a classifier to separate linearly separable data with any number of inputs. To visualize this, we're going to create some two-dimensional data to kind of see how this separation takes place. So this is just this is going to just randomly generate data, which is with the y-axis being the line which separates both the type of data points. So just arbitrarily define the x equal to 0 line to be the solution, so that it's easy for us to check whether our model actually follows through this. So over here we basically generate some random points on the x less than 0 and x greater than 0 side. And we also color these points as a red and yellow, and we plot them. So if you see a bit below, you can see the plot for the various scattered points. So the red and yellow are the two different types of data points. And we want our perceptron to find the right line which divides, which has all the red points on one side and all the yellow points on the other side. So that would help in distinguishing between the red type of point and the yellow type of point. So if you go down, we would have fed in the input data which we just generated into the model. And we see that every 500 iterations, it's going to print the error. And in the final iteration, we've also made it, after the final iteration, it shows us the graph. So if you remember earlier in the function, we had made it draw the current status of the line on the graph every 500 iterations. So originally you can see a line which is like very offset. It's not classifying at all properly. Then every 500 iterations, it's slightly orienting itself better and better to becoming the x equal to 0 line, so that it correctly classifies the red and yellow points differently. So this is basically a single perceptron unit. You can change the activation function from a step function to a sigmoid function, and you can also connect multiple perceptrons together to form a neural network. So if you would want to extend this, maybe you can define a neuron class which has a different activation function, or maybe you can define a layer class which has a set of neurons, and you can define a neural network class which has a bunch of layers and so on. So basically, this is the basic building block, and you can see that we've implemented gradient descent for a simple error function, which is the least square error function, and the derivative of that was easily calculable. So it's just 2 times the difference of the actual and predicted output. So we could directly substitute that over here. But in the future, when you have more complex functions, which you can't calculate general derivative, you should probably define a function which helps you calculate the partial derivative. And in order to do that, you could just change the value of one of the variables slightly and divide it by the value you changed it by to calculate the partial derivative. So then over to Kishore, who will be showing the implementation of the optimizers.
Yeah, so now let's look at the implementation of the optimization of algorithms. And so first, I am importing all the required modules. So we need a torch module for neural networks and PyPlot for plotting. And then there's this library called sklearn, which stands for scikit-learn, and it provides nice data sets, and also it provides functions for processing the raw data. And yeah, so here I have defined the data set. So we take the diabetes data set from the sklearn datasets module, and here the x is the data, and y is the target. Target is nothing but the actual value, and this is a regression data set. So we're going to we are going to predict some outputs through this network. And so yeah, first I use the train test split function to like split the actual data into training part and testing part. And this is a standard scalar object, which is SC, and it is used to uh, scale the to normalize the input data so that it will perform better in the neural network. And this is used for the same purpose, just to transform the data. And yeah, we convert the given numpy arrays to torch tensors using this torch dot from numpy command. Then we define the hyperparameters, which are the number of epochs and the learning rate. And here I have printed the yout.shape and xin.shape. Xin.shape is something about the input data that we are going to feed to the network. And you can see it has 353 records and 10 features. Okay, so now let's define the neural network using the nn dot module. So this is a nice way to define the neural network. So here we define a class called net, and then we inherit the properties of nn dot module. Uh, and then first in the definite function, we uh, define all the layers that we need for the network. So the first layer will be self.fc1, which is the just a linear layer. And next we have another layer which is also linear. And third, we have another layer, and you can see these two the arguments that we give here. These are the inputs and outputs for the layer. So so what self.fc1 equals nn dot linear, this statement means is that we have 10 input nodes, and the next layer has 10 nodes. So and we are fully connecting these two layers. And then we define something similar. So again we have another 10 nodes, and these are connected to the previous layer. And finally we have another 10 nodes and one node, and these are fully connected. And the activation function that we are going to use here is the ReLU activation function. And this and then we define this for function for propagation. And first the input passes through the first layer, and then we pass the information to, I mean the values to the ReLU activation function, and then again goes to second layer, then ReLU, and third layer, and then we get the output. Okay, so now let's look at gradient descent. So how do we implement gradient descent in PyTorch? So first, for plotting purpose, yeah, I defined np dot a range, and this will give an numpy array with values is 1, 2, 3, 4, 5 till the number of epochs. This number of epochs, this value, the second parameter, the second argument value is generally excluded. So we'll have values till number of epochs only. So that's why we have this +1. And then next we have y plot equals just empty list, and we'll update it. And next we'll have to make an object out of the class, so net class. So this will be the neural network that we are going to use. And the loss function that we are going to use here is the MSE loss, which stands for mean squared error. Why? Because this is a regression problem, like I said. So we use MSE loss, and then we need to define the optimizer that we are going to use, and we are going to use the torch.optim uh, function to define the optimizer. In this case, we are using SGD. And okay, this is gradient descent only, but then the optimizer is called SGD, and the difference you will see in a bit. the difference between the implementation of gradient descent and Minibasque gradient descent and STD you'll see in a bit. So here, yeah, the important thing is, so the syntax is important, and like basically in all the optimization algorithms, uh, the major part of the code is the same. We have the same neural network, and then we do the same forward propagation, backward propagation. The only difference is going to be the optimization algorithm which we are going to use. So this syntax is the only one that's different. So here we use SGD optimizer, and the syntax will be the model parameters, which are nothing but the weights and biases, and we have to give the learning rate. We have defined the learning rate as a hyperparameter here, which is 3 minus 4, and then we pass the input value to get the prediction, and this prediction is without training. Without training the data, we pass the input, and then just to check the error that we are getting before training. So yeah, this is prediction. This is the prediction before training, and before training we print the loss. And then for training, we use a for loop with number of epochs for like n iterations where n is number of epochs. And then again we use forward propagation, loss function, and back propagation. Uh, for back propagation, you would have seen these commands in the previous session. Uh, so we use loss dot backward uh, to perform the back propagation, and optimizer dot step to take a step towards the in the direction of direction opposite to the gradient direction. Yeah, so this is the gradient descent algorithm, and in case of gradient descent, uh, yeah, so yeah, in case of gradient descent, we get this kind of graph. So if we run this, we'll get this graph. So you can see error before training is this much, and error after training is this much. And the code is pretty much the same for all the other algorithms, except for the fact that the optimization function will be different. So then next we have to look at something called the Minibasque gradient descent. Uh, in Minibasque gradient descent, we send the data in batches instead of sending it one by one. So here we define the number of epochs as 1000, and we use the same neural network. We don't change the neural network here. The same thing. We are using the same neural network, and yeah, and same loss function. And is there a doubt? Okay. Uh, Yeah, and we send data in batches, and as Ishan explained, we have to first group the data into batches, and then feed the information to the network, and calculate the loss function and perform back propagation. So I'm defining this as the batch size. So which means in this is the batch size. So and each batch will have 16 data points, and the number of batches will obviously be total number of data points by 16, because each set has 16 data points. So there'll be int of the length of the input, I mean the total number of records divided by the batch size. And again, so yeah, so only this part will be different compared to gradient descent. Uh, so here we have another for loop to iterate over the batches. So again, we take we have to select data in batches. So for that we slice the data set in this way. So that will be, so batch x will be x in, and then the number of records will be I mean not number of records. So the index will be batch into batch size to batch plus 1 times batch size. So this is how we slice the array. And by slicing the array, we create data in batches, and we also create similar batches for y out, and then we again perform the same perform back propagation, and then we take a step in the direction opposite to the gradient descent. And yeah, so that is mini batch gradient descent, and you can see this is the graph. And yeah, so for all other optimization algorithms, the code is exactly the same, except for the fact that, like I mentioned, the optimizer syntax will be different. So let's look at that. For Yeah, so for momentum, the optimizer function will be the same as SGD, but then we have to mention another parameter, which is momentum, and this value generally we give it as 0.9, because the value 0.9 generally gives good results, so we give 0.9. And next, for RMS prop, the syntax is torch.optim.rms prop, and this alpha is nothing but uh, the uh, the beta that we saw in the exponentially weighted moving average, and this EPS will be this is nothing but the epsilon, that epsilon that I mentioned before, that is used to prevent the step size from exploding to infinity. And so yeah, it's just a very small number, and yeah, so the rest of the code is same. And next, we have AdaGrad, and for AdaGrad, sorry, yeah, for AdaGrad, uh, we don't have to mention that beta like we did in RMS Prop, because we just took the sum of the squared gradients in the denominator. If you remember, we didn't take the exponentially weighted moving average, so we don't have to define that alpha, but we have to define that epsilon again, and the syntax is torch.optim.adagrad. And yeah, we get, and then we finally in all of these codes, we finally plot the x plot and y plot. That is nothing but the yeah. So we plot the loss with respect to the epoch, number of epochs. So uh, this yeah, we plot the error with respect to the epoch. And then next we have ADA delta, and ADA delta is similar. So the syntax is just torch.optim.ADA delta, and here we give rho instead of alpha, but this is just the same as the beta that I mentioned before. For some reason, they use different variable names for these different optimizers. And the epsilon is again like we define it as 1e minus 1. So, and then finally, we also have something called Adam. Adam is very similar to very similar to Ada delta. Just a small. We have some mathematically. We have some different formula, but it's almost similar to Ada delta. It's a combination of RMS prop and the Allegret. And this is the syntax, just torch.optim.adam. And yeah, so that's it. That's how we implement. So basically, the codes of all these optimizers are the same except for the optimizer function. So if you understand this Minibasque gradient descent, yeah, then the uh, other codes will be clear. So, if, do you guys have any doubts? Okay, I think there are no doubts. So, and that's it for the session. Thank you for joining in.